All right, so I want to talk about path independence, but I couldn't remember how to spell independent, so I threw in some wildcard vowels where those are the appropriate vowels. It's definitely spelled right now, by definition. Okay, so I want to define path independent. Can you guys tell me what path independent should mean? We've talked about this a bunch, right? But what does it mean for a vector field to be path independent?
No energy gained.
Hang on, sorry. A vector field F is path independent when, okay, now go.
When no energy is gained or lost.
When no energy is gained or lost.
When moving a certain curve.
When moving around a certain kind of curve. What's the kind?
A circle or
Closed curve? Does that make sense? Like we just defined this word as closed, so let's use it.
okay.
So anytime you go around in a circle, right?
Yeah.
Anytime you go on a closed curve.
So the line integral of the closed curve would be 0.
Perfect, yeah. So when the integral over C closed, right? That's what this symbol means. So you're going around the circle of F dotted with dr is 0. So that's one definition. How else could I state this? We could say or. So this is right, either this, when I go around in a circle I get 0, or
The difference in any two paths is between the same points. Is 0.
okay. So the integral over over the curve C1 of F dotted with dr minus the integral over C2 of F dotted with dr is 0 for, now what'd you say about C1 and C2?
If they have the same starting end.
Yeah. For C1 and C2 from A to B. Right? They both go from the same A to the same B. You guys see that? Of course, we could rearrange this one a little bit, right? Algebraically equivalent would be to say the integral over C1 of F dotted with dr equals what?
Same thing with C2.
Yeah, the same thing with C2. Okay, so why are these the same thing?
You can apply the fundamental theorem.
So I don't know necessarily, and it's true, but I don't know necessarily that path independent is the same thing as is the gradient or something. You guys see that? It's true in reasonable cases, but I don't know that. So why are these two statements, right? The integral around a closed curve is 0, and the integral from A to B, regardless of what path you take, is the same. Could we draw a picture that we could see that?
Can we say that a closed circle could go either way, and that could be C1 and C2?
Good, yeah, we can do that. So maybe if we thought of A and B, right? And we had, like, here's C1, and over here is C2. Where's the loop that I can make out of C1 and C2?
A to B through C1, then B to A through C2.
Yeah, perfect. This business, right? You guys see that? That's a curve C. So if I know the integral around a loop is 0, right? Then I say, okay, if I'm considering paths C1 and C2 from A to B, well, I do C1 forward, backwards C1. Sorry, I motioned that the wrong way. Forward C2, Shimi, Christmas. Forward C1, backward C2 is a closed loop. So I know that's 0. I fiddle around a little bit with signs, I get that thing. Or if I know that thing, right, then I can make a closed loop, right? I can always think of a closed loop as two halves, and then I can apply this to the two halves. You guys cool with that? So either way of phrasing path independence, right? Either when you circulate, you get nothing, or any two paths between A and B give you the same answer. Either way, those are the same thoughts for path independence. Cool? Kind of follow?